Okay, folks, we're section 5-3. This is recording number 2. So I was trying to explain here. We've got this example here. We did it the hard way. Now we're going to try to use this formula here. Okay. So as you hopefully will recall, when we were talking about combinations, we had n choose. We said n choose r. Now we're saying n choose x. The formula is exactly the same. There's nothing sacred about using r. There's nothing sacred about using x. The concept is you have n possibilities, or n trials in this case, n trials, and you are selecting x of them. Okay, so the number of ways to get x successes from n trials, and you don't care about the order, so it's combination, is this: n choose x combinations. So on the top you have n factorial, on the bottom you have n minus x factorial times x factorial. This is the first part of the binomial formula. That's right here. That's how many ways can you get this stuff here. Okay, so let's take a look now. So that's the first part of the binomial formula. Now, each success has a probability of 1/2. Each time you have a success, it's always the same probability, so that's p, and you have x successes. X is the number of successes, right? So if you have x successes, it doesn't matter how many there are. If it could be 50 successes. So it'd be p times p times p times p 50 times. It's going to be the power here of x, okay? So that's what he says right here. Each success has a probability of 1/2. Can occur twice. Okay, I think it'd be more clear if he said it. Instead of saying it can occur twice, we should say it must occur twice. In other words, for this experiment, or to get this outcome, that's what we want. We want to find the probability of getting exactly 2 heads. So we must occur twice. Each success must occur twice. You have to get a head and a head 2 times. Each failure has a probability of 1/2 and must occur once. So it's going to be, I'm going to make you dizzy going up and down on this website here, but Q is a probability of failure. So if you have x successes, you must have n minus x failures. Let's use a different example. Let's suppose you had 10 events, or not 10 events, I beg your pardon, 10 trials, okay? So n is 10, and you wanted to know what's the probability of getting 3 successes. So it'd be p to the power of 3, and it would be q to the power of how many? If you have 3 successes out of 10, you must have 7 failures. So it's n subtract x. It's 10 subtract 3 successes. Okay, so plug in a couple of numbers and it becomes abundantly clear, I say. All right, so the number of ways of getting this number of successes is right there. Where did I leave off here? Okay, so you put it all together, and that yields you the binomial probability formula. Okay, so what it kind of boils down to is this probability over these two terms, these are called factors because they're multiplied. We say they're terms if you're adding them. We say they're factors if they are multiplied. So this guy times this guy tells you what's the probability of getting, x successes and n minus x failures. Okay, that's that probability. This first factor here tells you how many ways can that happen. We don't care about the order, so therefore it's a combination. Okay. All right. Now here's a very important point. When sampling is done without replacement, such as in a survey, the events are dependent events. Okay, so you would look at this and you'd say, well, hey, you're doing it without replacement. One of the requirements, one of the criteria, singular is criterion. So there's a criterion of the events have to be independent. Well, if you do sampling without replacement, you would very easily criticize me, and you would say, hey, Mr. Cantrell, you did this sampling without replacement. Therefore, the events, hold on one second. I want to go back up here to the actual definition here, okay? So if you do the sampling without replacement, the outcomes are no longer independent, right? The outcomes are no longer independent. So you could criticize me and say, hey, you can't use the binomial formula because this is not a binomial experiment, right? That's a very legitimate criticism. Let's go back down again. Well, what do? Well, what we do is we say, you know what? It's close enough for government work, all right? The binomial distribution, it's called the binomial theorem in some contexts. Or, I'm sorry, it's the binomial distribution, excuse me. The binomial distribution is so useful that we kind of fake it sometimes, okay? So that's what he's talking about right here. If sampling is done without replacement, as an example, surveys, you don't ask the same person this question, twice. You ask them one time and that person is no longer in the sampling, right? The events are dependent events. So you really should not be using this, right, according to the criteria that we have up there. However, the events can be considered independent if the size of the sample is small enough. If the size of the sample is small enough, then when you take one item from a large number of items and it's not replaced before the second item is selected, the change in the probability of the second item being selected is so small that it can be ignored. And the criteria that we use, or criterion that we use, is we say the size of the sample has to be smaller than, it has to be 5% or less. It's no more than 5% of the size of the population. So let's take a look here. Survey on doctor visits. 1 out of 5 Americans says he has visited a doctor in any given month. If 10 people are selected at random, find the probability that exactly 3 will have visited a doctor last month. Now, I wish the author would have written down the formula here. It would be a lot more clear. I can't write it on the screen, but take my word for it. Write down that formula every single time. So the probability of success, P of x, is equal to n factorial over n minus x quantity factorial x factorial. So here's the first part. That's we call this the binomial coefficient. Then it's the probability of success raised to the power of how many you want. The x. So it's p to the power of x, and then it's q times to the power of n minus x. So if you do this about 5,000 times, you have the formula memorized. Okay, so we plug in these numbers, and here's what we get. Okay, so how is this justified? Why don't you challenge me? Why don't you say, hey, wait a second, you know what? This is not a proper binomial experiment. Well, the reason is because we picked 10 people. We picked 10 people out of the millions and millions of people that are in the United States. So do you really think that not replacing changes the subsequent events in any significant way at all? Of course not. It does not change anything. So that's the rationale behind this. Okay, so the same exact concept here, talking about a survey on unemployment. You pick 5 teenagers. Okay, you want to have at least 3 of them are part-time jobs. Again, you're doing this without replacement. So in some technical sense, they're dependent, but we're going to go ahead and we're going to ignore that. Okay, so to say that at least 3 of them have part-time jobs, 3 out of the 5. So it's a probability of 3, probability of 4, probability of 5. So you just crank it out. You just plug it into the formula. And again, do me a favor and write down that formula every single time. And then you crank it out, and here's the numbers. And then you can add them up. After you add them up, that gives you 0.162. At least 3 teenagers have part-time jobs. You see, it's at least 3. So it's 3 or it's 4 or it's 5. So that's why you calculate each one of those and then you add them up. Okay. All right. So this is, to say the least, a true statement here. It says computing probabilities can be tedious. All right. Very tedious. So what are we going to do about this? Well, you can use a calculator, which I don't recommend, or you can use a website, which I do recommend. There's plenty of websites out there that you just type in the numbers and it does a calculation. But in the old days, what we used to do was we used tables, okay? So we would use a table for this stuff. Now let me see if I can, gosh, I hope I can do this right. Okay, here's table B. Oh, all right, I'm gonna have to pause. Okay, so what's going on here? The electronic version of the book, when I try to go to this table, it gives me an error message. I think you saw it a moment ago. So what I did was I have the PDF version of the previous book, the previous book's edition. So I have that on the screen right now. So I'm going to use this. So I hope if you're at home watching this, I hope you're following along in your book. Okay, so what he's doing here in example 519, he's talking about how to use these tables. So we're going to bounce back to example 516. That's one we did a moment ago. 516 is the one where we're tossing the coins. We toss it 3 times, and we want to find the probability of getting exactly 2 heads. Okay, so n is 3, x is the number of successes, that's 2. Probability of success, the numerical probability of success is 0.5, and so forth. Okay, so now what do we need? What we need to do on this is, you know, to really solve it using the formula, you have to calculate and do the, you know, do that binomial coefficient. Sometimes it gets to be hard, a little bit tedious, and so forth. Or we can use a table. So that's what we're going to do now. Here's his example. He says use table B, blah, blah, blah. Okay, so now let me show you the real table. Okay, so there's the table. It's in the back of your book. Okay, so this column right here, that's n. That's the number of trials. That's 3. And we wanted to know what's the probability of getting exactly 2. Not as, so out of the, let me get this. Give me a second. Okay, so n is 3. So what's the probability of getting 0 successes, 1 successes, 2 successes, or 3 successes? What's that probability? Well, it depends upon what p is. If p is 0.2, you know, here's a little table here of the probabilities of getting exactly, let's say, x is equal to 2. Okay, so let's do the problem that is in the book here, this example 519. So probability is 0.5. We want to know what the probability is of getting 2 out of the 3 successes. So you go on this row right here, come over here to the appropriate column, the column being 0.5. See, there's 0.5, and the answer is 0.375, which is exactly what we got before. All right, so that gives you an illustration here of how you can use that table instead of doing the calculations, okay? Okay, I'm going to keep working on these examples. I might have to do a couple of tapes here, but in fact, let's, example 5-20, I'm almost out of time on this, so let me stop this recording and we'll do the next recording starting with this one. So this is the end of this tape.